As we're already running a bit late, I'm going to try to keep it short, but now we want to go on talking about some fuzzing, as Dan already touched on, and he, I think, already brought up some of the very interesting issues that also came up for our work, and also the problems that we are tackling because of those observations. For example, what he was talking about is that we kind of need systems to be easily fuzz testable in order for us to be able to test them. And the other thing that he said is that there are different kinds of input types that we have, and we're going to talk about pretty different ones that you might be interested, or than you might be expecting, or than you might know yourself in here, and which are very interesting from my point of view, and which I have put some research into. So this talk is called Fuzzware, Automating and Scaling Fuzzing for Firmware. And this talk in a nutshell is going to be something like this. So we want to take in some firmware from binaries that come for IoT platforms or little small embedded systems, which are just a bit smaller than what you would expect and have a bit of a different format than what you would normally be used to. And then we put this kind of firmware into the cloud, and there is a lot of things going on, but we will get into this later. And then we want to get bugs out of it. And this talk is about how can we achieve this and shed some light on this. So first of all, who are we? We in quotation marks here for the moment, as I get into. My name is Toby. I'm a PhD student at Ruhr University Bochum. I'm also a CTF player, Pontoon participant before, and I'm interested in binary exploitation and reverse engineering. In my research, I'm focusing on firmware here. Normally, Marius also wanted to join us here, but he sadly cannot due to COVID reasons, but he's recovering quickly, and he's also sending his greetings. All right. First of all, let's understand a bit about systems that we are going to talk about today. Embedded systems. So what do we understand by embedded systems? A lot of you might think about something like a router that they have at home, anything that's kind of close to what they're using. And those systems, what they do is they run Linux a lot. And sometimes, or most of the time, it's a bit of a boiled down Linux in the form of a busybox or so. But then we figure out this type of embedded system is not the only one. And there are a lot of other systems out there with very different properties. As we can see here, we have different types of embedded systems. Some PLCs here, which you would find in a factory deployment, or an ECU, which you would find in a car. And then finally, on the further right, you find some home automation appliances, which get smaller and smaller. What all these devices have in common, that they usually do not run any Linux. So they are very hard to kind of grab your hand on, but we still want to have some security analysis of these as well. And we'll get into why this is a bit tricky to do, and how different ways that we could go about doing that and analyzing them. So first of all, in order to do this, we want to understand how do these systems actually talk to the hardware around it. Because if we do not have a Linux system, kind of the hardware still has to be talking to or be spoken to by the firmware, and we cannot just have a Linux syscall and then have a read or something that we can get our input. We do not have a file system, things like that. What do we do in this scenario? And as it turns out, we have three main ways of communication between the firmware image and then the hardware that's surrounding it. And one of these is called memory mapped input and outputs, or MMIO for short. And what this is basically doing, it's a magic memory region, which doesn't really represent any RAM as you would see it in a normal computer. If you have just RAM memory, you write something in, you read it out, and you get back whatever you got. But instead, what is behind this is an actual device, and it's talking to you. And depending on whether you do a read on this magic memory region or you do a write, you can either find something out about the state or read some data out of this peripheral, or you can put some configuration in. And this very much depends on how this MIO is laid out, but we'll talk about this in a bit. The second mechanism which we have at our disposal for talking between firmware and hardware is interrupts. And this is basically a doorbell sign where the hardware can tell the firmware, okay, buddy, I have something going on, please check on me. And what's happening in the firmware then is often that you have something that's called an interrupt handler, and the interrupt handler will check on the device using MMIO and see, okay, what's going on? Do I have a new network packet coming in, or things like that. And then we have the third kind of mechanism, which is called direct memory access, or DMA for short. And here we have some communication mechanism for high throughput scenarios, where we have something like an Ethernet card which has to run very rapidly, or USB or things like that. And in these cases, what the firmware and the hardware do is basically they unify on a memory region which they want to talk through, and then they can both simultaneously read and write to this memory region. And then, of course, for example, if a device wanted to send something like an Ethernet frame and make it available to the firmware, it could just write something into an Ethernet frame buffer and then give an interrupt, and then the firmware knows, okay, now I can access this directly without having to use MMIO to finically read out every byte one after the other. And this is what kind of reading input would look like for us from a normal fuzzing perspective, for example. We have a get char, so we want to read a single byte of user input. And this is pretty straightforward in Linux. What we can do is just have a read sys call, pass in standard in as the file descriptor 0, and then just get our value back and return it from the function. However, if we look at the same thing now for the serial interface of an embedded controller, for example, this would look much more complex in this case. And we can see that we have already talked about some MMIO, and here we can see that 3 different MMIO registers are actually involved in reading this. And so it's much more involved to do, and we have some talking to the hardware to do in here as well. And we'll go into what exactly this is doing in a bit, but let's skip this for now. So with these kind of basic things out of the way, then we want to go to rehosting. And first of all, we want to define what rehosting is. So I just read it out here. It's the automatic creation of virtual execution environments for embedded firmware. So what we basically want to do, we want to take some piece of firmware out of the device and run it somewhere on a general purpose system. For example, an emulator, something like that. And there are many reasons for this, for why we would want to do this. And we could go into all of these details, and we actually wrote a paper about it. Remember, I'm dabbling in some academia, but we do not want to do it here. And instead, we want to take it down to something a bit more streamlined and maybe easy to understand, and also the main reason, quite frankly, why we want to do this. So on the one hand, we have those smart things, so-called smart things, such as a lightning bulb or a temperature sensor. And these things, we do not really get an SSH shell onto there. We cannot deploy AFL and then just run some binary on there. We have to have a bare metal system, which just doesn't allow us anything in the traditional means. And they are very slow as well. So I just got told outside here that somebody actually tried to fuzz test the router, for example, and that the chip was actually brown afterwards. So that's very cool to hear. So maybe we also don't want to blow these things up in the first place. And if we turn to something more powerful, like clock computation, then we can just deploy it on a massive scale. And whenever we get it into an emulator and actually are able to do this, then we can get fuzzing to a very potent level here. All right. So with these things, you might say, okay, Toby, you already said it. We have an emulator. We have the cloud. We can just combine this, right? So we just take the emulator that we already have. It's very good. It's scalable, and it's a community project which is developed and very mature. Why can't we just plug the firmware into QEMU and then just do some fuzzing on this, put some cloud service behind it, and the bugs will fall out eventually, right? But there sadly is a bit of a challenge with this. And this challenge is mainly consisting of the complexity of hardware devices that we are facing. And so if we think about the different vendors that would present or offer some device like this, every one of those vendors will have different devices that they offer. And then for every device, we have different peripherals. It wants to have timers, it wants to have a serial interface, it wants to talk via Wi-Fi and things like that. So we have all these different peripherals. And then afterwards, each peripheral also has different memory registers. And this kind of multiplies up. And if we kind of see what this entails in the documentation, which we sometimes have available, not always, then we can see it. The details are not really important here, but we can see that there are device regions, and each device region has a peripheral region, and then, which we do not even see here, it's different MIO registers, so kind of explodes. And some of these devices are fully implemented. If we look at some system, for example, a very well-established one like in Raspberry Pi, we have a full implementation of all these registers. But it's a huge amount of work. And if we think about that, we have all these small little devices which are not really covered by this. Then we might not even find an implementation in something like QEMU. And then what makes it kind of worse is that in a lot of cases we do not even have documentation. So even if we wanted to comb through like a 1,000-page document which describes all these things, then we couldn't do it even if we wanted, if we do not have documentation in the first place. So this kind of begs the question: we have so many devices and we want to secure the firmware that is running on them, and it's very hard to analyze them. So how can we automate emulating these systems in the end? And as it turns out, different people have looked at this problem before, and how can we kind of model this hardware for systems that are not quite Linux-like systems, and we cannot use any abstractions that we are used to, and cannot really apply the tools that we are used to as well, and which have also proven very reliable sources of bug finding. So one of the first things that I would like to mention here is what is called Pretender. So what they basically try is to take a piece of hardware, run it, and take some traces from it, and then try to understand, based on the traces that we have seen and that we know are valid, can we figure out how the hardware behavior works. And then people took it a bit further with p2m and partemu, where you take it in a fully virtual domain. You do not use any hardware anymore, but you see what the access patterns are in something like QEMU, but QEMU without actual devices. And then you kind of monitor what communication is going on, and then you may be able to derive from these access patterns what the behavior should be. And then people took it even further, where we use some program analysis techniques like symbolic execution to do this kind of modeling for us. So whenever we have an access, can we figure it out by analyzing this access and then seeing, okay, does the code tell us something about what we supposed to do? And then, of course, we're in 2022, and we have Fuzzware, and this is kind of the prototype that we want to talk about and the work that I've been performing. All right. So Fuzzware, rehosting via the fuzzer in the loop. So let's recap for a bit. What have these previous works done on a kind of broader level? So these prototypes have looked at this problem in a two-step way. So first of all, what we want to do is we take a piece of firmware and then we rehost it so that we can run it in an emulator. And then afterwards we can put a fuzzer to it and have the fuzzer do the security auditing for us. And the question kind of that's begging here is, can we also integrate the fuzzer from the start? Can we not treat it as a two-way process, but have the fuzzer in the loop directly? So the idea behind this would be that modern fuzzers are already very good at kind of identifying what is useful for a program. So we can take something like coverage feedback, and whenever we find coverage feedback within a program, then something is likely, or an input is likely to be useful for it. And the idea here is, can we use this for modeling as well? Can we just have the fuzzer do the heavy work for us and do this? But this, again, if we think about this a bit more, it has some issues concerned with it. And the first thing is that while not fully random, fuzzers still rely on a lot of rolling a dice, basically. If you look at the source code of AFL or AFL++, it's not quite 100% random, but the mutations try to modify it in a lot of ways, and what comes out is more or less a random behavior. And then this makes it very hard if you have a lot of choices to kind of find the right thing in the first place. And firmware makes it a bit harder still, because as we will see, there is a lot of low-level like firmware and hardware chatter going on, which kind of explodes the state space a lot, which is kind of needlessly so. And we'll see what this means here. So let's look at a code example. And what you can see on the left side, it's a function called perform_op. And then on the right side, we have the control flow graph, or CFG, that represents the different paths through it. So what we can see is that we have an MIO operation register which is queried. So the firmware will look, okay, what kind of operation does the hardware want to do, or what state is it in? How should I behave based on that? And depending on what operation comes in, we can step through this and see, okay, if we do the default case, it would do some housekeeping with some coverage here assigned to it. Then we come to the B case, and there is some special handling to it. Depending on the status, if it's special, then there is some special handling, and otherwise we have the default one. So we can step through this as well. So as we said, the idea is to kind of involve the fuzzer in here. So what do we do if, or how does this look like in case the fuzzer is choosing some values for us? And as I said, there is some randomness in here, so we can kind of say, okay, we just pick some values. It's not quite random in the normal case, but we just pick some random values here. And then we can see, okay, what kind of picks did we get, and we can highlight them here and then plot them in this coverage here. And the greener or the more dark green coverage node is, the more it was visited. And as we can see, we have some parts of this coverage not even occurring at all. And this might be problematic in case we have a bug hiding in some special case, for example, we do not get any coverage out of here. So this kind of begs the question, or brings up this idea of the paradox of choice. So on the one hand, we want to give the fuzzer all the flexibility in the world. We do not take away any paths, because especially the specific or special paths could contain bugs as well. But at the same time, if we give it too big of a search space, then we cannot really do anything. And the question, or the fuzzer will not be able to find them. And the question here is, can we reduce these available choices a bit? And this is where little Toby, on the start of the academic work, started going on the internet looking for some quotes for inspiration. And the first one that he found was, look for chances to take the less covered paths. And we had a second from the same author. We do not still or yet know who it was. It was, you will regret the paths you didn't cover. And then at the end, also a keep it simple, stupid. And as it turns out, it was already called our Lord and Savior by Dan before in the keynote. It was, of course, AFL, the little fuzzing, American fuzzy lob. And this kind of got me thinking. So you have keep it simple, stupid. So can't we kind of make this life of the fuzzer easier? Just make it simpler. And this is where kind of the idea stems from. And we can look at what this entails and looking at this code again. So if we look at this code as we went through, it was a case A, case B, and default case kind of scenario. So what the fuzzer should kind of be aware of is that there are three choices. We do not really have a big search space. We have just three choices based on our MMIO. And what if we change this representation for the little bunny a bit here, and then we just gray out the ones which do not matter. So we just have A, B, and C, and B is the representative for the default case here. And if we just let the fuzzer choose between one of these three options now, what we can do is go through the same scenarios again. And then we get A and B here, and then we get to, or A and default, and then we get to the B case. And what is interesting is that we have the same kind of situation here as well. We can kind of nest this idea. So here we have another if-else statement, depending on whether we want the status, the special case, or not the special case. And this is, again, just a choice between special and not special. So what do we give the fuzzer? If we could find some modeling approach which just gave us one of these two choices, we could just have the fuzzer choose the one or the other. And the interesting thing is that now it's much easier for the fuzzer to find all these different coverage paths, and this allows us to find bugs maybe. All right, this brings us to the modeling component of Fuzzware and the different models. And this, it turns out we have already seen one. So this is what we call the set model. It's it just gives the fuzzer, pre-computes a set of choices, and then the fuzzer can just choose between them based on some byte of fuzzing input, for example. And let's complete this picture a bit. So we have some more models in here. So let's look at this serial getC function again and go through these different lines a bit in more detail. So here what we can see is that, first of all, the firmware has to make sure that the hardware actually has some data available, so it stays in a busy loop until this data is available. And it will actually get stuck in this busy loop until the data is available. And in case we want to do fuzzing, it's clear we do not want to get stuck in any loops, we just want to go on. So what we do here is apply what we call a constant model and just have the the access return it has data. If we can show by some analysis that this is just being stuck in the loop without anything happening, then we can safely just assign the constant value and not have to involve the fuzzer. So in this case, we make it really simple for the fuzzer because it doesn't have to do anything in this case. And the interesting thing here is that we have a 4-byte access before, so the fuzzer would have given us 4 bytes, but now we have just 0 because we can handle it by ourselves. And this kind of applies to the second here as well. What we have here is that we have a GPIO value which represents something like an LED lighting up and indicating some activity on the serial interface, for example. And this is what we can see here is that this hardware value is first read, then modified and written back. And everything kind of stays in the hardware domain. So we do not really care about this because the firmware doesn't take anything into account in its logic. If we can show this again, we can just keep this as a normal memory access here. We call this a pass-through model. So whenever the firmware writes something and reads it back, it gets the same value. And the fuzzer still doesn't have to be involved in here. And then finally, we have this data access. We see we have a 4-byte access first, but then we are masking off only 1 byte. So we only have to have the fuzzer give us 1 instead of 4. And kind of if we summarize this, we can reduce the input space by quite a bit because the fuzzer, before it had to deal with all these different things, and without changing the program logic, we can just reduce it by over 90%. And kind of what we have now is we have a function which takes 1 byte of input and just takes 1 byte of fuzzing input as well. So it's very familiar to the fuzzer now as it would look like on a Linux system, for example. All right, if we put this together in a little diagram here, we have the full system overview. So in the middle, if you're not familiar with it, it's the emulator called Unicorn Engine, and what it gives you is basically instruction execution without any hardware components around it. So it's a stripped version of QEMU at its core. And what it's doing is just executing this firmware image, and then whenever there is any hardware accesses, it just forwards it to the fuzzer again. And then if we see any hardware access which we have not seen before, what we can do is have symbolic execution. In this case, our modeling component perform some analysis and see whether we can fit one of these models which we have seen before. And this kind of gets fed back into the emulator while it's running, and then it can afterwards handle some of the accesses transparently or boil them down and so on. And it's kind of a loop going on as long as we have more MMIO registers or kind of hardware interfacing that has not been previously discovered. And what we did is that we wrote a kind of complex prototype for this. It's about 10,000 lines of source code, and it's also available on GitHub. So with this, of course, let's get fuzzing. And what is important for fuzzing is obviously, and as an academic especially, to have very novel ideas about how to go about fuzzing. So having to set up something and then fuzzing something and afterwards triaging crashes is something that nobody would ever have come up with before. So we in the academia are all about giving some novel ideas to everybody, right? So that's what we did here. No, of course, what we at least do is that we supply some utilities for what we already know is required to do this fuzzing workflow. And without going into these right now in just theory, let's look at some examples here. And I have a little demo prepared. So what does it look like to use Fuzzware? So first of all, we want to do a work on Fuzzware. So we're actually in the virtual environment to use it. And then we want to configure, set up configuration for the binary file using Fuzzware genconfig. And then we can see we have some configuration files created. And I can now use the pipeline component to do some fuzzing. So after some setup, what we can see that, as we would expect, we have some coverage coming in, some translation blocks or basic blocks being discovered. And what we can see afterwards is that we also have some models being created. So this is the modeling component feeding back some configuration snippets to the emulator, which is then consumed by the emulator to set it up for a more efficient fuzzing workflow. And then if we wait for a little bit more, we find some more coverage afterwards as would be expected. And this is where we can also stop the fuzzer for the purpose of this demonstration. Then what we can see, we have a Fuzzware project directory which contains all these results from the fuzzing. And here we can query Fuzzware conf so that we can see what kind of functions have we already covered, and we can also replay an input based on coverage here and get the behavior of it. The second thing that we can kind of look at is the models that were created themselves, and we can see in the mio_config.yml we have different ones of these models. A constant pass-through, there's a set model in there as well, and so on. And then, of course, if we have run this for a bit longer time and not only 30 seconds, we can go into a project which has run for a little bit longer time and went through some configuration updates, and then we found some crashes, for example. Then we can also replay and analyze these crashes afterwards and look at what the behavior is. And then we can see here that we have the crash state, and then can see what the reason for it was. And in this case, we can see it's a bit of a messed up PC, so this is a stack-based buffer overflow in this example. But we're not going to go into this exactly. Okay, this is that for the demo. And let's go and look for some bugs that we found with it. So first of all, it's important what kind of system did we choose in the first place. And as it turns out, what we found interesting is kind of the systems which other firmware uses afterwards to build upon, and then have some embedded operating systems which come with a network stack, which then allow small power devices to be connected. And these are implementations of such operating systems which are connectivity driven, so Sapphire, RTOS, and then Contiki-NG on the other end. And it comes with a lot of connectivity features, something like Bluetooth Low Energy, Wi-Fi, 6LoWPAN. Different companies are behind this because they are interested in having a joint core of high quality software, of course, and they also have a security development lifecycle, and the team is also very cool to work with. So great projects, both of them. And we found some bugs in here, and we want to actually look at those. And as we cannot go into all these bugs in detail, we want to frame them in the terms of famous last words, or what the firmware assumption could have been just before this kind of issue occurred. So the very first one, let's start with this. It says these two objects will never be the same, which kind of resulted in one of the bugs which we had. Then we have a second one. We know something about something like a data structure or so in the program, and we can just do that, right? We can optimize our algorithm to do just that, work on these assumptions and make everything run very fast, for example. And this also resulted in some bugs. And then we have somebody else who surely have initialized this, or will surely initialize this. And especially across API boundaries, if you find something like this, it very much lends itself to bugs. And then, does anybody have an idea of what kind of category could be there as well? It has to do with something that I think a lot of people have seen before. This length can never be smaller than. This was actually something that occurred a lot, and then there is the King's category, of course. This length can never be larger than. So anything with missing bounds checks. And one of these bugs that we encountered, I would like to spotlight a little bit here. And this occurred in the 6LoWPAN fragment reassembly. And for some context, 6LoWPAN is kind of the way that smart and constrained devices can use to talk IPv6 to each other. So what they can do is they can send small frames over the air, but they are pretty small. So what you have to do is to plug different fragments together so you can have a full IPv6 packet. And what the standard says is that you have kind of a frag1 fragment and then frag-n fragments. So one is the first and then the follow-up frames. And as everything goes over the air, you cannot really rely on something to come in a specific order. So what you have to do is just you take everything in and then have to reorder it afterwards. And so then it's kind of a good thought to have. We already have a pre-sorted list, right? We have a frag1, so it's always at the beginning. So what we're doing is not really sorting a list, but we are sorting a list with the first element already in fixed place. And we can just assume that the first element just doesn't change. And it turns out if you generate an algorithm for this and do the sorting, what comes out at the end is an infinite data structure. It's a ring instead of something that's finite. And now you have an assumption about something being a finite data structure, and you start working on this. And this is where things get a bit weird here, because what you have to do in 6LoWPAN in order to put together the fragment data is that you have to strip the fragment headers from all of these different fragments. And you have to do it once, but you can do it once by just going through this finite list, of course. And if it's a ring afterwards, it's no longer finite. So you turn it into an infinite header removal. Packets get smaller and smaller over time. The integer of the size just gets negative. You have a really big mem copy, and then the firmware is not really happy about what comes afterwards. And the actual crash triaging here was a very interesting process. I find this bug interesting because I am sure I've looked at this kind of functionality before, and just to understand kind of what is going on in the network layer, and I'm sure I've missed this kind of bug here. And the whole triaging process was pretty involved, and I tried to dry running this with Marius and telling him about it, but it was kind of resulting in this scenario. And he said, okay, maybe we should not go into all these details. So I'm sparing you these details here. But instead, we want to get to some closing thoughts. And first of all, of course, what are the boundaries of what we can do, or what we want to do here as well? So first of all, it's a research prototype we have implemented for ARM Cortex-M. We are working on extending it, but for the moment, it's working on a very popular platform, but obviously it doesn't cover all of them. And then there are also special cases in firmware which we are just not this way of looking at this MIO modeling does not really cover, because DMA is just a different beast. It's an interesting problem, but something that we do not really cover here. And also, if we have some very specific assumptions about timings, then things can get messed up as well. For example, the emulator tries to make things go as quickly as possible, of course, but then at some points, for example, if you wait for some initialization or you are sure some device takes for a bit longer time, we may not always scale the timing in a correct manner so that things can come too early logically or maybe even too late logically. So if we have situations like this, some modifications are required manually. And then, of course, there's a bit of common sense in here. So in case you have a Linux system, and you can use what tools you have already available, just use the tools you have already available. So that should work. And then finally, one thing I would like, a vision of mine that I would like you to take home. It has to do a little bit, has to do something with the duck, and here it goes. If we want to convince firmware to walk like fuzzable software and then also quack like fuzzable software, then we might someday be able to actually give the tools to the embedded firmware development guys to do the fuzzing themselves and find all these bugs, so we don't have to do it for them, because currently we do not really supply them with the tools to be able to do it. And if we can do this, we can find a lot of bugs in the process. And with this thought, I would like to thank you for the attention, and I'm open for questions. Yep.
Test. So if I understand correctly, you drop in a firmware that you have no preassumptions about, and then it will automatically find out what hardware MMIO it does. But how do you deal with stuff that actually changes? Like, for example, if we take a Game Boy, for example, and we have like bank switching. So you write to an address and that changes RAM completely. Or as a more recent example, we set up page tables, which does virtual memory. How do you detect these kind of things?
So currently, this prototype doesn't do these things on the architecture level, which are kind of baked into the core of the architecture. So what we, for example, implement is the interrupt controller. So for enabling and setting priorities for interrupts, we still give this architecture level these architecture level components and this functionality, and have this done by the emulator itself. So what we can do then is that we can, if we know the architecture on a very broad scale, then we can create an emulator which has these core components in it, something which the architecture cannot do without, and would have these represented by that. And then the modeling of the MMIO afterwards would be something done via the models.
So you could adjust some of these things by hand for the emulator.
You would create these core components once, for example, for the for interrupt controlling and so on, and then do this to fuzz test any component which is working on this kind of base architecture. Yes.
Okay, thank you.
And regarding the differences between piece of hardware and interfaces, I saw that you have kind of profiles based. Yeah, the tool use profiles where you can take from documentation the addresses and you handle in this way, right?
Yeah, what you do to set the base emulation up is that you supply some base memory ranges in that case, that you kind of tell it, okay, where can you expect hardware accesses to be, and then where can you expect some RAM to be, and where's the code loaded. This is kind of the base assumption that you need to know where are things based quite roughly. Not you do not need to know where some MIO registers are or any ranges like this, but you have to know the broad memory range where things could occur, and then listen for these accesses.
Okay, no, I was asking more specifically if you're providing addresses for specific interfaces. Yeah, okay, thank you.
We can also talk about this afterwards. If I have not understood your question correctly, that's very fine. I'm sure it's a good one, so.
Hey, thanks for your talk. Group never disappoints. Maybe I didn't get that right, but how do you create the constraints for your model? Is this manual work, or is this being computed with like?
I didn't explain the one symbol on the right, which was the symbol for anger, and it was maybe it was implicit from my side, but it's dynamic symbolic execution that we're using, kind of in the context of we're taking a snapshot of what's going on in the emulator, and then just look at this very specific access and just have to step a couple of times to not kind of have to run through.
Completely automated.
Yeah, this is all complete. Yeah, very good. Which we also saw with in the demo where these models popped up. It was also an automated process.
Would modeling not be useful by non-firmware software?
Yeah, I think this is also a very good question. I have not always said that, but these questions were really good and valid. This one is actually something which we could also apply in non-firmware environments. The bit different, or the kind of difference here, is that for MIO accesses, what we have is an access which is very local and very short-lived. So we have one MIO access to a register, we use it, this operation, for example, and then discard the value afterwards. So what we can do is we can do the analysis in a very confined space. So we don't just have to look at this one function or some basic blocks of this function to see what it does. What we could also do for software in the non-firmware space is that we have this type of model as well, and then fix some values in place, for example, or have some kind of grammar description maybe coming out of this modeling that we say, okay, this field can either be that or the other one, and then we have the fuzzer just give us some input, and then we look at these fields, and then based on what the fuzzer gives us, we insert the right choice and kind of do the same modeling, maybe in place of where the input starts being fed in, or maybe in the place of the fuzzing process itself, where we inject some code or like some listeners or things like that. I could see that, yeah. It just has a bit more. It's not that natural to do it in that case, because it just has it has a broader frame. You have to trace the data for a longer time. But in general, this is, it's a good idea. All right. I think there are no further questions. If you have any questions, we can talk outside as well. So thank you again, and have a good break.